Hello, everyone. My name is Diana Chavez, and I would like to welcome you to today's BeConnect webinar hosted by Visteon. Visteon is a $3 billion a global technology company that designs, engineers, and manufactures innovative cockpit electronics and connected car solutions for the world's major vehicle manufacturers. Visteon has approximately 10,000 employees at more than 40 facilities in 18 countries. We are headquartered in Van Buren Township, Michigan, and have been in Querétaro since 2017. In 2019, Visteon finished construction on a new facility called Visteon Technical Center Querétaro. The 6,000 square meter world-class engineering center is home to highly skilled software, hardware, and mechanical engineers. Here, they develop advanced cockpit electronics products to support Visteon North America customers such as Ford, Fiat Chrysler, General Motors, Nissan, and Honda. We encourage you to learn more about Visteon and explore the open positions we have in Querétaro by visiting www.visteon.com/careers. Today, we are joined by four panelists, including Bradley Corbin, Systems Tech Fellow, Numa Hernandez, Systems Engineer, José Raúl Rodríguez, Principal Systems Engineer, and Andrés Vidales, Senior Systems Engineer. Hmm. We encourage you to submit your questions to our panel both during and at the end of the presentations. With that, I'd like to turn it over to Brad to begin his presentation.
Okay, first I'll introduce myself a little bit. I'm Brad Corbin. I've been working at Visteon for 25 years in systems engineering, and prior to that, I worked at defense industry in systems engineering for 8.5 years and 2 years in validation. I'll let Numa introduce himself now.
Thanks, Brad. Hello everyone. My name is Numa Hernandez. I've been part of the system team in Visteon for over 6 years, and then, basically I've been working in different projects, mainly focused on driver information and audio infotainment. Previous to Visteon, my experience is mainly focused on development of embedded systems for over 3 years. So now we can introduce José Raúl.
Hello, I'm José Raúl Rodríguez. I've been in Visteon for 2 years. I've been working as a systems engineer for around 12 years. I've worked in different lines like HVAC, infotainment, driver monitoring systems, and driver information. So I'll introduce Andrés Vidales.
Hey everyone, good afternoon. My name is Andrés Vidales. I've been in Visteon for 1.5 years now, and I'm part of the driver information group, developing requirements for Ford North America clusters mainly. Previous to that, I worked as part of the systems team for Aptiv, developing Bluetooth and media requirements for infotainment head units, specifically for FCA. And today I would like to, because I'm so relatively new to the company, I would like to share some of the differences that we have, that I have found, the way Visteon does things when compared to the other company that I work for, and why I think it's so much better. So hopefully this is what I'll be focusing on. And having said that, I think I'm going to hand it over to Brad so we can begin this webinar.
All right. So at Visteon, we've been trending over the last 20 years, working up a different approach to systems engineering, where we are feature-based systems engineering. So instead of developing a specification for an entire program or project or product, we have feature specs that we release independently. This allows us to do platform and OEM bookshelving for features. We have universal SRD development where all of our specs have the same read for everybody. So it doesn't matter what program I'm on, what OEM I'm on, or if I'm working on a platform or a project, it all looks the same. We have, in my experience over the last 30 some years in systems engineering, there's really different methods for lower level systems. And basically you're taught that a system is a system is a system, no matter what level. Use the same methods, use the same techniques at all levels. And I found that's just not really true. At the high level vehicle level, you know, textual requirements stating we want these features and we want this performance level, that works great at the vehicle level. It doesn't work once you get down to defining distributed systems where functionality is separated amongst different components and you have lots of interfaces. Once you get there, textual language really doesn't work. And if you're a global company like we are in 18 countries, you know, you textual requirements just don't work. The feature-based approach allows us to be ASPICE level 3 and Agile compliant, and we also incorporate some model view control partitioning. Some of the other things that we do that are interesting is we have a systems team forum where the entire systems team in North America meets, and we all share, and we'll talk about that a little bit later. And we do tools and modeling as required. This allows us at Visteon for the systems engineer to have a big picture look. So when you come in here, you understand the product. You understand the features and how they work, how they interact with each other, and how they fit together in the vehicle throughout the entire life cycle of the product, from manufacturing to service and field support. You understand product performance, you get domain expertise, and you get to apply systems engineering that has 4 major outputs that every product development organization needs to have from some group in their company, and it should be the systems group. We provide a single interpretation of customer requirements to the product development teams. So the 5 users of our specifications get one spec with one interpretation done by the systems team. So we will work with the customer to identify things that are not defined well or not totally have enough information. This allows us to provide a complete set of implementable, testable, and unambiguous requirements. Provides the same read to all the product development teams across products, OEMs, and programs. And it's componentized by feature and feature group, which leads to agile development. So we can release an individual feature by itself. And the way that we can do this is a little bit unique. You've probably seen diagrams like this before, showing how you start from the customer requirements and get into a product design that fits in a vehicle with vehicle interfaces. And this is correct, except we add in this product functional architecture in this red box up here. And this is a functional architecture. It's independent of hardware and software. There are some hardware components in for certain drivers, but in general, this is independent of hardware and software. So we have predefined interfaces that we use to allow our independent feature development.
Yes, and one of the things that when I joined Visteon, what I find is very useful is that, you know, because we're dealing with complex projects or complex programs, you know, we really know that we have to break it down somehow, right? And one of the things that I've been learning throughout this time is that it's really about breaking it down into the correct pieces, right? So this product functional architecture that Brad is talking about, it's broken down in a way where you can see all the different components that are gonna interact within your system, and so you get this definition that's complete, right? Instead of going through the development, sometimes figuring out that something is missing, this is the first thing that you see. You figure out how everything is gonna interact from a high level, and then the work becomes getting those detailed enough so that they can be implemented. So having this really gives you a good perspective of how your system is going to work, right? And as Brad mentions, it's independent on specific modules that are going to get implemented, but you get all the functionality at once, and it's something that's really helpful, and it's something that I didn't experience in the past, right? And as Brad mentioned, it's something that makes things special, and I think it gives the entire team the idea of the product they're working on. So it's something that's really unique about the way that we do things in Visteon, and it's something that I found very useful for all the teams throughout the development process.
Right. So also on my experience, well, when I started on this systems team, I realized that one of the benefits on having this approach is basically that as a system engineer, you need to do much more than just requirements, right? Because normally there is this misconception on that systems team or requirements team only handles customer requirements and just that, but instead doing the analysis of the entire system allows to have a better idea on how the product should work and how everything else is impacted, right? Either some functions or even the team. So the product development can be centered in this kind of definitions, and allows also, as Brad mentioned, reusability, as we will see later.
Yeah, architecting a product like this allows us to do a lot of reuse of the features that we develop, the blocks that we work on, and that has its benefits. It saves time. It reduces the chances for mistakes. And in order to come up with an architecture like that and have requirements to fit in that kind of architecture, you really need to understand how the system works. Right. So this is something else that having this kind of architectures helps. It helps systems engineers and to understand really what the system should do.
Yeah, and one additional aspect here on this type of product functional architecture is precisely that it is not tied to any particular technology, right? So that is, in my opinion, like the main benefit on having this type of architecture, where you can have similar products or n number of products with different type of features, and then you can develop those features with a platform, right? So it's not tied to any specific hardware or technology. So that is very useful for reusability as well.
Right. So I'll quickly go through and show some examples of 3 different domains. So we have a driver information functional architecture where we have across the top, we have ECU level type features that or functions that touch every feature and have an interface with almost every feature. Those interfaces are predefined. And then that allows all of the features to have these predefined interfaces from the ECU level, which makes the feature development easier because you're just focusing on the functional logic. All of the rest of it has already been done and completed and input. This allows for reusability as well. There's a climate control product functional architecture. You'll see it has the same bars across the top along with climate control functionality. Here's an IVI product functional architecture. very similar, same bars across the top. There may be a different network thrown in there, like MOST or Ethernet or something else, but the basic concept is the same. Those things feed into the features. And then if you look at, want to integrate it even some more, here's the domain controller with driver information, IVI, and climate control. And they share those same interfaces across the top. In fact, most of the ECUs in a vehicle are pretty much have the same architecture. So when you take that approach, then a lot of things become a lot easier. It's a little more abstracted, but once you get to thinking that way, things become a lot clearer and a lot easier, and you can focus on the functionality of a feature better.
Yeah, and well, if you can go back one slide, I think one of the things I believe this type of functional architecture does is, most of the times we're working on a small part of this entire system, and so it's easy to get lost just on that specific thing. When you have something like this, it really helps create awareness as to, the part that you're working on, the part that you're defining or implementing or testing, but it also gives you an idea of how that part contributes to the entire system. So for me, this serves not only helpful, to have this functional architecture, but it's sort of like a roadmap of what the product is meant to do. And you can always locate where you're working on. And I think that really helps get the system's perspective, right? As Brad mentioned, I think, it takes some time to get used to it, thinking about this things this way, right? But as he's showing, there's 4 completely different architectures, and yet all 4 have very similar structures. So once you get into this type of mentality, things just become more clearer. So I think this is very, very, very useful to have functional architectures for any product that you're developing.
Right, and one additional point here is that we can see the patterns, right? So one of the main activities that a systems engineer or a system architect needs to do in the very early stages of a project is precisely to define this type of diagrams or definitions. So, but we can see here that the pattern is that such that we have some dependencies, or we create dependencies based on fixed interfaces. So that is going to allow also having like a better definition for every feature and function, and not only from the functional perspective, right? I think that this also can help from a management point of view to, for instance, plan a project knowing that, okay, if you have a defined number of features to be supported, you know in advance what are going to be your dependencies, right? So from your customer specs, you need to start mapping to this architecture what will be the parts that are going to be satisfied by, and then it will be like a suggested way on doing or progressing over the period of the project, right? And then after this is developed, I also think this is useful, for instance, from a maintenance perspective, or when some defects are found on the field. One way to think about this is that, for instance, if you start checking from top to bottom, start debugging like the functionality, you can find more easily the what is the issue, right? So I think in that sense that this type of architecture gives not only the main idea on how the product should work, right? It can give also the perspective for planning and debugging.
Okay. So one of the basics that we have is performing our feature processing in certain orders. So we start with the generic product level processing that gets all of our inputs and our power modes and our operating modes. Then we provide our configuration, diagnostic logic as inputs into our features and functions that we have on our particular program. We have our individual feature functional logic and a feature group diagnostic logic. And then we have some kind of manager or arbiter or queue or whatever is applicable that controls which of these pieces of logic or configuration or power mode or whatever is going to control the feature and output it to the view. So this is kind of basic, but it shows the power of a simple architecture and a common architecture with defined interfaces.
Yeah, one of the things that I really like about this slide is that, as you're mentioning, this is it looks very simple, but yet there's so much behind it that I think it's something that's important to break down. You know, in my experience, most of the times when you get an spec from the OEMs, they usually just talk about the feature, right? So they describe how the feature is going to work, and you know what the user is expected to do. But then they reference all these other things like voltages, like CAN signals, like power moding and stuff like that. But those are usually treated separately, right? In my experience, one of the things that I was missing was precisely having this system, this entire system awareness, right? I was very much focused on the feature in my previous job, that, you know, all these other things, I got an idea of how they work, but because they were not predefined, sometimes I had to make assumptions about, you know, well, I expect this to work this way, but sometimes, you know, the feature may be different or has something specific that was not considered. And so this leads to sometimes a lot of rework. Having this defined the way that it is, you have your generic product level stuff that all your features are going to use. And then, you know, within that feature group, like you can take a warning, right? You can define the best warning possible, but if you don't have some sort of logic to define the manager or the arbitrator for that, then that warning is not going to play nice with the other warnings. And so if you take a look at it from a system perspective and have all these predefined interfaces, you're not only able to develop good features, but as Brad mentioned in the beginning, because you have these predefined interfaces, you may be able to even spot stuff from the customer specs that are missing. And so that's something that's really important. You know, it looks very simple because it's just like a one pager of what it does, but this really spreads out to all the development and makes, you know, feature development much simpler because it's very modular. So you can take and add features as you want because you already have your core functionality for the manager and for the generic product level, and that makes it easier to have better products that are more scalable and that have better reuse.
Yeah, I completely agree with you, Andres, and especially in my experience on those days where I was initiated as system engineer. I remember dealing with a number of customer specs, and then the first challenge is, of course, understanding how the feature works, right? But then as you go through the analysis, then you start wondering, okay, what is missing? What possibly can be undefined? Because normally the customers really want to have a good traceability between your requirements and their specifications, right? So again, by having this type of architecture allows you to spot those missing parts, or even if something is not properly defined from the customer, you can, of course, tell them that something can be improved, right? So that is also one of the main benefits on having this partition architecture with very well-defined interfaces. And then the part on having these individual, let's say, boxes is that precisely one of the main challenges on having an architecture, a platform-based architecture, is that once a project starts reusing some of these different features, the main challenge is precisely on analyzing that those interfaces are declared properly or published properly, right? Because one of the main things that I've been seeing on using this approach is precisely that you can have a very good definition on how the feature should work. But then at the moment you implement it on a certain program that not necessarily uses all of those defined interfaces is when the problem starts, right? So this type of architecture also allows to have certain flexibility on the use of those interfaces. So in that way, you can cover like the different situations or configurations that a feature can have, right?
Okay. One of the things that we do for every feature and every feature group is we create an architecture diagram that takes from those previous blocks that we showed for the product architecture and shows what interfaces are used, where they come from, who uses them, and what's the output. So we have an architecture diagram for every single feature that shows this. And these are examples of our predefined signals that we use on all of our features. So we have our voltage signals, our power mode signal, our own network signal inputs, which we rename so that the customer can change their names. They can move them from message to message or move it from CAN to LIN. I don't care, whatever they do. That's not going to change my downstream feature processing. So no matter what they do or how they change it, my feature processing, my feature logic downstream of that input signal, since I use my own name, I don't care. And we do things that are signal based, not message based. So when they move it from one message to another, it doesn't impact our functional requirements.
So one thing is that to highlight here is that we have different levels of architecture, like this network multiplex. This is like a higher level, and that block number 2 network multiplex has its own architecture inside. We try to separate what is common to what is unique, and that allows us to reuse a lot of our algorithms. Just feeding parameters or extra information, but most of the functionality is already structured. And as Brad mentioned, one of the important things is that, like, for example, all of the OEMs use different power modes. They may use different power modes, and that could be contained within that power mode determination block. So the differences don't propagate to the left to the other components in the architecture.
Right, and another thing that I found very useful about dedicating, so much time to the architecture is that this is really the thing that's driving the development. So whenever someone's working on a feature, whether they're developing the architecture or they're working with, the software team or the validation team, having this type of diagram, this architecture diagram, really helps out because it gives you a sense of how the entire feature is going to work. So you can take a look at what you'll need to modify or what inputs you need from the different modules in order to make your feature work as expected, right? Back in my previous experience as systems engineer, this is something that I didn't realize I needed because there were architectures, but they were not as detailed and not with these predefined interfaces. And a lot of the times you'll have to come up with these diagrams in order to explain, because even though you have something similar like in your head, taking time to write this and having such level of detail really helps all the teams get in sync as to what the feature is meant to do and how it's meant to work. So the fact that we take a lot of time to develop these architectures, and it's really the thing that's driven the entire development and the entire definition of the system, it's something that, is one of the highlights that I would say I've seen in my time in Visteon.
Right, and yeah, so I also would like to add here that in my time in Visteon, sometimes I have heard that people asking me, "Hey, why your system guys define this type, for instance, the network signals, right? Why do you provide a specific name to that, and you don't use the names directly from the customer? And the reason is that it will be a really bad practice if we do that, because that can have like severe results. For instance, if we were based our product definitions directly from the customer, we will be expecting that if they change something, it will be very hard to maintain our definition or even the software, right? So for that reason, we try to split whatever definition the OEMs can have to a common definition within Visteon, right? In that way, we somehow abstract some parts from the customer definition, but keeping the real expected functionality, right? So that's one of the important things that I see on having common interfaces, right? That is basically like the concept on having that, and also, of course, that also allows to a better understanding, right? If we see a signal called power mode, we will always expect to have a defined domain on that value. So we don't care about how it is processed, right? That is determined in another part. The important is how that interface is used in certain features, and then you focus on the functional logic, as Brad was mentioning earlier.
And when you receive a requirement from a customer, like a functional requirement that has defines a feature or a function, in order to implement that requirement, to translate that requirement to this architecture, you have to break it down, right? So to do that, you have to understand what the feature needs to do. Then you can break it down and fit in the pieces into the different components that are already predefined. Like a piece may go into the power mode determination block, a piece may go into the network component, the piece may go to the HMI component. So you have to understand you have to understand what the OEM wants, what the customer wants, and then you have to understand the architecture so you can break it down into the pieces and make the functionality happen the way the customer wants, and fitting it into the architecture.
And we have architectures that are as simple as this TX architecture with just a few blocks to architectures with 50 blocks. And for some features, we'll add a block diagram where we'll show all of the tables and diagrams in a feature SRD and all of their inputs and outputs, so that you get a flow for the entire SRD for some of the more complicated ones where we have 100 blocks and all of their interfaces are listed. The other thing, as the guys were mentioning, just stated a different way, is you take the customer requirements, you have to mold them into our architecture. So you have to understand the customer requirements in order to do that. And since we're doing that up front as the systems team, we don't have to wait for software to start coding before they say, I don't understand this. Because the way that we do systems engineering and compile our specs here, if that's not clear, that'll be clear, that'll be made known to the systems engineer up front before we even get to code. So example of our requirements that are non-textual, this is a sample. And so basically, when you're reading the customer requirements, you're going to do an analysis, and like any good, college course or whatever, you have to state things in your own words using your own terms. And if you can do that, that shows that you understand. So we translate textual requirements or ideas, partial diagrams, whatever the customer gives us from many different sources into a design or into a set of requirements using design language that we have to make sure it all works before we can go further. So, I mean, here's just a couple examples, and this one shows our our overall manager handling the high level ECU inputs.
Yeah, for me, one of the things that was, some of the more challenging ones at the beginning, but it's also some of the most rewarding, is getting an idea of how to start thinking in terms of these diagrams or tables. Because once you get to that point, and because we've been talking about everything being done with predefined interfaces, and because we have all these architecture diagrams defined, this leads to the requirements only have a single interpretation, right? When you're using text, as Brad mentioned at the beginning, sometimes interpretation can be a big problem, because we're all not experts in doing technical required writing, and even if we were, there's always subject to interpretation. With this approach, the logic can have mistakes or can be wrong, right? You cannot escape that if your design is not okay. But the thing that you can avoid is having this subjective discussions about what the statement is meant to represent. Because it's a diagram or a truth table, you only get one interpretation, and it makes things easier in terms of the implementation, but also when you're debugging like a hot issue, it takes away, like the ambiguity that may come, right? It's either right or it's wrong, right? And if it's wrong, we'll fix it. And if it's, wrong in the implementation, that'll be fixed as well. But there's no middle ground. So having non-textual requirements is really a really big deal for me. It's one of the best things that I've seen in terms of approaching requirements. And it's only possible because of all the other stuff that we're mentioning. If everybody had their own, diagrams, they may work, but when those features interact with other features, then that's where the problem may come in. And the fact that this is like I see it like the last step towards having a single interpretation is because this is the final detail implementation description, and all the other stuff support that to make it better for the entire team. And having a single interpretation is a very big deal, when you're developing a complex program. So
Okay, so this is a requirement or a set of requirements that it's within the architecture, that fits in the architecture. And one of the things that I like about this is that you can see that we have a common processing, right? All OEMs have missing signals, and you may have to do something different on when a signal is missing, but the processing of the signals are the same. We have signals that may come with an invalid data or a range that is invalid. So trying to, one thing that we do is we try to separate what is common and what it's unique, right? And you can configure the things that are unique into summary tables, into different specific flow diagrams that fit into these blocks. So I just wanted to highlight that writing requirements like this and having a good architecture and understanding different OEMs and how, for example, this thing, how CAN works, you can do things like that, right? Defining requirements that are reusable.
Right. And one additional thing that I would like to add is for those who may be wondering what kind of modeling tools we use here in Visteon, is precisely this type, right? This is one example, right? Like the regular flowchart diagrams, but also as Jose Raul mentioned, we can have different logic tables that can be represented in or developed in simple Excel spreadsheets, or even more complicated models also can be modeled using not sophisticated tools or expensive tools, or even a specialized modeling language. What we try to do here is, again, provide a universal meaning on a specific requirement and not tied it to any specific technology, right? So I think that's one of the most also important things to consider here.
Right, and we have models in Excel, we have models in MATLAB, Simulink, Stateflow, whatever. We do some features that have auto-generated code, and we have developed tools like if you want to do a truth table We have a member of our group that developed a tool where you can put in all of the inputs and its states, all of the outputs and its states, and it'll compute a combination of every possible input, and then you have to fill out the outputs, and then the tool will also reduce it. So we develop our tools as necessary as we go. So there's no lack of that. Lastly, we have our systems development process, where we analyze the information we get from the customer. We have a feedback loop for open issues, and that's done by the systems team. The system team provides the single feature SRDs based on our bookshelves, our product bookshelves, our platform bookshelf, and our OEM bookshelves that are used by the rest of the product development team to build the product. And this process, is something that we've developed over several years, and we have a systems forum that we discuss anything and everything inside that process. All views are welcome, no matter if you've been here for 1 day or 30 years. We like to hear different perspectives and make sure that we're always striving to make our stuff better and more unambiguous, cover more things, and make sure that we have everything covered.
Yes, one thing that I would like to mention real quick about the systems team forum is that, in my experience, what I'm mentioning is, you don't usually get that chance to have this level of interactions with all the team members from the systems team. And, people are very knowledgeable, but are also very willing to share that knowledge, which is not sometimes the case, in all companies. So the fact that we have the systems forum, and the fact that, people are so open and willing to share that knowledge with you, just speaks to why we're always striving to do things better, because it's not my knowledge, it's the knowledge for the team and for the company to make things better. So I think, that's been a very good experience for me, being able to talk to all the people from around the world and get their inputs, and seeing them so willing to share their knowledge. That's something that has been, really a great opportunity for me. So.
All right, no other comments, then we can entertain any questions that you might have at this time.
Now it is time to take questions from you. As a reminder, to ask a question or make a comment in the chat, click the Ask a Question button on the bottom of your screen. So here's the first question. How the platforms are correlated with systems architecture, principally when starting a new program?
Okay. Since we have predefined interfaces, what we usually do is we'll work with an OEM for a while, and we'll develop our OEM bookshelf requirements. And during that development, as Jose Raul mentioned with the network processing, we find that we've developed a set of network processing that we can use for every OEM, for LIN or CAN or the basic network inputs. So then once we have a design like that, we move it into platform. The specific things for platform development would be any hardware specific related items. We do have like standard voltage processing, standard hardware I/O processing, standard network I/O processing. That's independent of hardware platforms. So we can use those things for any platform that we have that's new. So we already have a baseline of getting all of our inputs into our features based on the processes and the analysis that we've done over the last 20 some years, where we've come up with these algorithms and methods that we can have a good base. And like I said earlier, when you focus on a functional architecture, you find that those common inputs like diagnostics and configuration and all your input and output processing. That's pretty much common, and it's pretty much independent of hardware. The hardware just adds a little extra, okay, I have to do this in order to get signal A from processor A to processor B, but it doesn't change the fact that signal A has to get from the functional logic to the view. Whether the view is separated by 2 processors or 2 separate modules in a vehicle network, doesn't matter. That signal still has to go from the functional logic to the view. And Andres, you want to add anything?
Oh, okay.
Anybody?
Yeah,
Anybody?
so just, I don't know, can you hear me?
Yes.
So yeah, so we also have system requirements unique to platforms, to different platforms or different customers. So that's one way that we handle. If I understand your message, your question is how do we map signals or how do we track signals that are being used across different customers? So we have unique requirements, set of requirements for each program, right? Where we say all of this set of signals are used in this platform, specifically on this platform, or may not be used, right? So that's one way of tracking or differentiating what are we using, what signals are we using, and which signals are we're not.
Thank you. Another question is, how do you maintain a map of the signals used in architecture with the different customers' implementation? How do you deal with the use of different protocols for the same signal in terms of safety or CS?
Well, I'm going to assume that by signals, we're talking about the ones that we show in the diagram, like all the different outputs and inputs. And if that's the case, I think that one of the important things that we talked about during this webinar is the fact that we're not doing it just based on the OEM specs or on the OEM input. One of the things that we try to do is look at it from the entire system. So it's not just going to be, if different OEMs have, things that are specific, right? You can probably accommodate those within our architectures. But for the most part, we can reuse a lot of the stuff that we have, and we try to keep it in a way that the architectures and the signals used throughout those architectures, right, remain common, because we're developing things not just specific for the OEM, but overall for like a cluster, let's say, right? So there's going to be things that are common, and then you can add on to that by modifying the architecture to accommodate something that's very specific for an OEM. So, and I don't remember the second part of the question.
So yeah, I can answer part of that. The cybersecurity, how do we deal signals with cybersecurity? So we have like a TARAS per feature, right? Not necessarily per feature, but we have a TARA for the inputs and outputs and the affection of those features, and we identify all the critical data, all the critical functions, and we list them, and we link each of those critical data to a summary of the critical data and the critical functions to a feature. So when you have a program that is using that feature, it's already linked to a set of predefined or set of signals and variables and features that are secure, and we have mechanisms for those. So you have also a set of mechanisms that you can use for protection, and you do that in your specific platform or a specific program requirements, set of requirements.
And I'll add that there are some things that we develop that are common across OEMs, like speedometer. So we have a common signal name that we use for, I don't care who the OEM is. This is the speedometer input signal, and here's the speedometer output signal. So we go even cross OEM in many of our internal names for common features. So it works quite well, or the concepts work well. What you run into in different OEMs is that they'll add certain features. Toyota will add turn signal control for the entire vehicle in the cluster, or some body functions or whatever. So you get those various combinations. And if we have functional safety, or we have, like camera monitoring for driver alertness, things like that. Those are just another feature set that gets integrated into the backbone of the infrastructure that we already have laid out. It still has interfaces with all the rest of it. So it once you have this functional architecture with functional interfaces, it makes a lot of this a lot easier to integrate new things or different things or whatever.
Thank you. Another question is, how do you manage those OEM's specific requirements that are not possible to abstract?
So we have requirements like HMI graphics, or some OEMs will give us models, and then from which we have to develop code from. So those, we have our requirements capture tool. We use Doors Next Gen. Those all go in there. We link to those. We have structures and methods and processes in place to manage those items. We have what we call, we have OEM SRDs, and we have application SRDs. And the application SRDs are those things that may use an OEM bookshelf SRD, but they get certain configurations or certain aspects of our SRD or our feature applied to this program versus another program. Or it's a new thing, like all the HMI is pretty much application specific. I don't know if I answered your question or not, but
just to clarify, an SRD is a system requirement document.
Thank you. The next question is, for a new feature architecture that needs to be created, how do you manage the time that you spend into creating a detailed architecture versus not delaying the project development because the product architecture is not ready?
So we can do and then once we have it done for the next programs, we can have the time to develop the architecture and reuse it on the next programs. That's one way to do it.
And I can tell you that doing some quotes for different OEMs and even different domains, the time it took me to do product functional architecture was not very long, a day, for something I've never seen before, because the basics of an automotive ECU architecture are pretty much the same. If you look back at the slides I showed earlier, there's the horizontal bars across the top that interface to all the features, and then we have the gray boxes for this is the way how you display information. So I don't care if I'm climate, audio, DI, center stack, HUD, just a standalone display. Those elements are already there. They're there in every product. The things that are different are the features. So if I have common feature interfaces between those elements, then all I'm really left with is developing my features. My infrastructure, my overhead, from a functional standpoint, is predefined. Now, when I get into hardware-specific architectures or software-specific architectures, the way those get implemented may be different, but the signals between the features and those elements are the same. So it doesn't take that much time.
Yeah, one thing that I will also add to that is that, sometimes it seems like developing the architecture for, like, let's say a feature for like the ones that we show, um, it's going to take a lot of time, and it's going to take that time away from the development of the actual spec. But I think it really should, one of the things that I've learned is that you should really think about it the other way around. If you have your architecture well defined and you spend enough time in it, right, the development of the specifics is going to be not only much simpler and much faster, it's also going to prevent problems in the future. Like if you start writing your requirements and you don't have your architecture well defined, you may be missing things, right? And fixing those later on in the project may be even more time consuming than taking the time initially to think it out throughout and to develop it in that way. So that's another thing that I found. You have to sort of switch your mentality a little bit, right? And dedicate enough time for the architecture, and everything else will flow much faster and much easier.
Thank you. Another question is, how aligned is your current development process with, example, ASPICE capability models? Is traceability something already embedded as part of your architectural creation process?
Yes, it is. We're SPICE compliant. We do traceability.
Yeah, when we were doing ASPICE audits and compliance checks, parts of our company were developing a single feature to walk through to show ASPICE compliance that took months. When the ASPICE auditors came here for the first time on our first program, they said, okay, what feature would you like us to walk through? And we said, I don't care, pick one. They said, no, what feature do you want us to walk through? And we said, I don't care, pick one. With this method of development, we were ASPICE compliant from the get-go. So we don't have to do anything special for ASPICE compliance. All we have to do is explain our methods and show how our development process works, and they go, oh, okay, because everything's there. In fact, we have a more complete set of requirements than almost anybody else I know of. And I've never seen this type of work in any other place, but we're very ASPICE compliant. And this method of feature-based design flows into software almost directly. In our requirements management tool, Doors Next Gen, we do have traceability either line by line or at the header level if the customer requirements aren't broken up to provide individual requirement traceability. But you'll see that we go from customer requirements in text or diagrams or whatever format they have into our fixed format. So we'll have a lot of many-to-one and one-to-many trace links. But all of our bookshelf items that we're working on for our OEMs, if they provide individual requirements, we will have line-by-line traceability, requirement to requirement traceability.
Yeah, one additional thing that I would say is that, the traditional way, or the way that I experienced ASPICE before, it's really all about the metrics, right? Like you get your requirements and you have all these attributes and links to stuff, and that's the way you ensure compliance. And it works, but the thing is, because we're doing all this other stuff first, right? The architectures and the predefined interfaces, right? The level of compliance, right? I think it's much better, because when you're doing attributes and you link between the different customer specs and whatnot, you can show that you're linking to stuff, but the actual compliance to the customer requirements, which in my opinion is the actual goal for ASPICE, it's not really there. So doing it this way and having all these predefined interfaces, all these architectures, it just makes us, as Brad mentioned, being ASPICE compliant, like it really flows naturally. it's not something that, the first time you take a look at it, you may think that there may be stuff missing, but the reality is that it's much better just because of all the work that's done prior to the A-Space compliant audit. So.
Yeah, one other comment on that as well is if you take the traditional systems engineering approach, you have a requirement and then you have a myriad of attributes. We don't use attributes. We have some mandatory ones like for ASIL indication or variant or something like that, but we don't use attributes. Our attributes are distributed based on our feature partitioning and the interface is defined. Because really, when you think about it, if you take a single requirement, you're adding attributes to define how that requirement fits with all the other ones. But with our predefined architecture and our predefined interfaces, all that work's already done. So we don't need attributes. So when you come here, you're not going to sit down, take a requirement, copy, paste it, and then spend, a day figuring out attributes. We don't use attributes in the RM tool.
Thank you. At this point, we have come to the end of the call. On behalf of Visteon and our 4 panelists, I'd like to thank you for joining us and for your participation in the discussion. If you are excited about what you learned today and a career at Visteon is something that is of your interest to you, we encourage you to explore the open positions in Querétaro by visiting www.vistion.com/careers. Again, I thank you for your participation. You may now disconnect.